In this portion of the course, we're concerned principally with trying to improve our critical thinking skills. So we're presented with arguments on a regular basis. People try to persuade us of various conclusions. They're trying to convince us that their way of thinking about things or their way of doing things is most appropriate, is most sensible. And good critical thinking is required in order to distinguish good reasons for accepting some conclusion or policy recommendation versus bad reasons, identifying bad reasons or bad arguments. You may already have looked at the PowerPoint that concerns informal fallacies. Informal fallacies are very useful when we're trying to develop our critical thinking skills because these name and help us understand mistakes or errors in reasoning that happen very regularly, that are common within dialogue, within discourse, within debate. So when we're reading people's opinions or editorials, we're reading articles, or when we're listening to speeches, we need to be attentive to the possibility that informal fallacies are being committed. If you're not yet sure what informal fallacies are, or you need examples of informal fallacies, then looking at the PowerPoint presentation and textbook should be helpful. But one of the limitations of studying informal fallacies for purposes of improving critical thinking skills is that informal fallacies are inevitably presented in natural languages, in English or Spanish or French or German, but some naturally spoken language. But one of the things we know about natural language is that it's often ambiguous. So there are different ways of interpreting what people say, either orally or in writing. Some phrases are just ambiguous, vulnerable to reasonable competing interpretations. And so when somebody argues for something, and when we suspect that they may be committing an informal fallacy, there's often a worry that perhaps we haven't quite understood what it was that they were intending. So what one person says may differ from what somebody else understands or takes them to be saying, understands them to be saying. So this is an obstacle towards evaluating people's arguments when we might not be quite sure exactly what they're trying to express. Another shortcoming of natural languages when it comes to argument evaluation is that there may be some hidden assumptions in people's arguments. So they're trying to convince us of something, they're assuming certain things, but not explicitly expressing those things, and so it's difficult to evaluate their argument because there are these hidden assumptions that perhaps they suppose are plausible and reasonable, but we might not be so sure about those hidden assumptions. So the role of these hidden assumptions can also be an important obstacle towards evaluating people's arguments. There are ways around these obstacles of ambiguity and hidden assumptions. And one way around it, one influential way to try and avoid these problems, is to invent or create a new language that doesn't have these features. A new language where there is no ambiguity about the meaning of different sentences. A new language where hidden assumptions are not permitted. Every assumption, every step in an argument is made explicit. And when we do this, we start engaging in different logical systems. One of the most important of these logical systems is deductive logic. And so over the next lecture or so, we're going to introduce deductive logic, look at some of its features, because looking at deductive logic can be an important tool for improving our reasoning skills, our critical thinking skills, our argument evaluation skills. So I talked on the previous slide about deductive logic as introducing a new language. If we build on that idea, deductive logic as involving a new language, then one thing we want to know is what's the vocabulary? What kinds of things does this logic use? And the basic vocabulary of deductive logic are simple sentences. So we build up complex sentences within deductive logic from simple sentences. And the simple sentences are denoted with lowercase letters, usually starting with P. That tends to be the convention. The grammar of the language is also fairly simple. We have special terms within our logic, and the four that we're going to be concerned with in this course are those of not, and, or, and finally, if then. And you can see here on the slide that we've got special symbols that are used to denote these connectives or operators or special terms. Deductive logic is sometimes known as symbolic logic because it makes such heavy use of symbols. So now that we have our simple sentences, and now that we've drawn attention to these special terms, then we can combine them to build up more complicated sentences. So let's allow that P denotes the English sentence, "A spider ate Harry's bagel," and we'll let Q denote the simple sentence, "Harry is hungry." These sentences, by the way, are what's known as declarative sentences because they declare something. They make a declaration. And this is actually a requirement on our language, on our logic, that the simple sentences make some declaration. So that precludes from our simple sentences things like questions or promises or commands, for example. But these two examples are good instances of simple declarative sentences, and so we can use those in conjunction with some of our special terms to build up more complicated sentences. So, for example, the sentence in our deductive language, or in our symbolic language, P dot Q, translates into English as "A spider ate Harry's bagel and Harry is hungry." So the dot denotes the English term "and." P and Q, as we've seen, denote respectively "A spider ate Harry's bagel" and "Harry is hungry." So we now have a way of translating either from English into our symbolic language or vice versa, a sentence like P dot Q or "A spider ate Harry's bagel and Harry is hungry." Another example, this one utilizes the not operator, and the way we denote this within the symbolic language involves placing the symbol first and then our lowercase letter following the symbol. I like to call this this symbol the gate, but you can call it whatever you like, really. So if we've got gate Q, then that's going to translate into English as "Harry is not hungry." Or perhaps you could read it as "It is not the case that Harry is hungry." But the more natural way to express that thought would be "Harry is not hungry." Moving on, now we have an English sentence, "If a spider ate Harry's bagel, then Harry is hungry." Well, we have a symbol, sometimes called the horseshoe, to denote if-then sentences, And so now we can translate this English sentence into our symbolic language as P horseshoe Q. So the if part of the sentence comes before the horseshoe, the then part of the sentence comes after the horseshoe. So any sentence in English, if something, then something, can be translated into our symbolic language, assuming that what's associated with if and associated with then are declarative simple sentences. We can reverse the order of a conditional sentence, an if-then sentence. So here we have Q horseshoe P, which translates into English as, if Harry is hungry, then a spider ate Harry's bagel. So hopefully now you've got some sense as to how translation works back and forth between our symbolic language, which is so important for deductive logic, and a natural language such as English. It's probably a good idea at this point to play around with these ideas a little for yourself. So think up some simple declarative sentences and then construct some more complex sentences using some of those terms like not, and, or, if then. Since we can translate sentences from English into our symbolic language, then we can also translate entire arguments from English into our symbolic language. Because, as you should have seen in an earlier PowerPoint presentation, arguments are sets of sentences where one of those sentences is recognized as the conclusion. So let's take an argument in English and let's try translating it into the symbolic language. If we inspect the language in English, then one thing we'll notice is that it contains two simple declarative sentences within it. These are David is English and David is Australian. Notice that David is not Australian isn't for us a simple sentence, because the word not is something that has a special symbol. So we don't want to denote the sentence David is not Australian with a lowercase letter and ignore the gate symbol. So here we have then our two simple declarative sentences that are contained within the argument. And now, given the special terms that we've already introduced, we can complete the translation from English into the symbolic language, and what we get is something like this. The or connective, you'll remember from the last slide, is denoted using a V, or sometimes called a wedge. So the first sentence in English reads either David is English or he is Australian, so we can denote that as P wedge Q. David is English or David is Australian. The second premise in English reads David is not Australian, and since we have a symbol for not, then we can translate that into the symbolic language as gate Q. A symbol I haven't introduced so far is the symbol for therefore, which is a symbol that has three small dots that look like they're the corners of a triangle. So since our simple sentence David is English is denoted with P, then we can complete this translation with our three dots followed by the letter P. So what we now have is a translation of an entire argument from English into the symbolic language. Let's look at another example. This one reads, if David is a philosopher, then he is not a banker. David is not a banker. therefore David is a philosopher. Take a moment to see if you can identify all the simple declarative sentences that are contained within that argument. Hopefully you've seen that there are two such sentences, and so again we'll use P and Q to denote them, and in this case we get P to denote David is a philosopher, and Q can denote David is a banker. Now we can go ahead and complete the translation, and what we get is P horseshoe gate Q. For the second premise, gate Q, and for the conclusion, we get the three dots followed by P. If you're unsure as to how we got this translation, it's probably worth pausing and figuring it out for yourself, trying to understand it for yourself, because we are going to be building on these translations, and so it's important to keep up with things as we proceed. Now that we are able to translate from English into the symbolic language and vice versa, we've started to set the stage for evaluating arguments, determining whether arguments are good or bad. And one important distinction to bear in mind when evaluating arguments concerns two different ways in which arguments can go wrong, two different ways in which arguments can fail to persuade, fail to convince us of their conclusions. One of these ways in which arguments might go wrong concerns the plausibility or truth of the premises within the argument. So premises might be true or false. An argument that relies on false premises shouldn't convince us of the truth of its conclusion. So if someone is trying to convince you of something, and the premises or evidence or reasons that they adduce in favor of that conclusion seem to you controversial or just straightforwardly false, then you're not going to be convinced that their argument is a good reason for accepting the conclusion. You might agree with the conclusion for other reasons, but our concern, of course, is with evaluating arguments for conclusions, not simply evaluating the merits or plausibility of the conclusions themselves. The other way in which an argument might fail to persuade is if the premises don't stand in the right relationship to the conclusion, such that even if we thought the premises were all true, even if we were convinced that the premises are reasonable, we still wouldn't find them good reasons to accept the conclusion. Within deductive logic, we talk about this feature of arguments as concerning their validity. Arguments are either valid or invalid. Valid arguments are ones such that, if the premises are true, then there's a sense in which the conclusion must be true. Invalid arguments are ones whereby, even if the premises were all true, it wouldn't necessarily be the case that the conclusion was also true. So what this tells us is that a valid argument can have some or even all false premises. Here's an example of an argument which is valid, but it has a false premise. It's valid because if these premises were all true, if the sentence expressed at 1 and the sentence expressed at 2 were both true, then the conclusion would have to be true. But this has a false premise. We know that premise 1 is actually false. So it's a valid argument that has, in this case, one false premise. invalid arguments can have all true premises and a true conclusion. To illustrate, consider this argument. Some cyclists have taken performance-enhancing drugs. We have good reason to think that's true. Lance Armstrong is a cyclist. We have good reason to think that's true. Therefore, Lance Armstrong has taken performance-enhancing drugs. Well, we have good reason to think that that is true. So, all the premises are true, the conclusion is true, but this is not a valid argument. It's not a valid argument because the truth of the premises doesn't force the conclusion to be true. To see that this is the case, just consider some other professional cyclist who has not taken performance-enhancing drugs. So try to bring to mind some cyclist who hasn't taken performance-enhancing drugs. And now let's substitute that character in for Lance Armstrong. It would still be true that some cyclists have taken performance-enhancing drugs. And it would be true of our substitute that they are a cyclist. But it would be false that they had taken performance-enhancing drugs. So an argument that has this form might have all true premises but a false conclusion. And what that tells us is that even if the premises are all true, it doesn't force the conclusion to be true. And so this is an invalid argument. So what we've seen with these two examples is that whether an argument is valid or invalid, and whether an argument has all true premises or not, are importantly different questions. Knowing that the premises are all true or knowing that they're not all true doesn't tell us whether the argument is valid or invalid. They're different kinds of quality or property. Now, what we're most concerned with in logic is the relationship between premises and conclusion. And so within deductive logic, what we're concerned with is whether a given argument is valid or not. We've been talking about this informally as concerning whether the truth of the premises forces the conclusion to be true. But there's actually a better way to think about validity. And that's what we're going to start talking about now. And it's a way of thinking about validity that relies very centrally on what's known as the form of an argument. We'll introduce in a few moments the simple method that enables us to identify the form of an argument. But let's just first talk a little about why we prefer this way of understanding the notion of validity. So, up until this point, when I've talked about valid arguments, I've suggested that a valid argument is one in which if the premises are true, then the conclusion must be true. And what might be dissatisfying about this definition is reflecting on the idea that the truth of certain sentences must or may not make another sentence true. How are we to evaluate this idea that the truth of certain sentences must make something else true? There is some room, it seems, for ambiguity there or confusion, and so what we're going to introduce now are some alternative definitions and a more rigorous strategy that doesn't rely on this idea that if some things are true, then other things must be true. Okay, so let's start with some definitions then. And the first of these describes how arguments now are going to be considered valid if they're instances of a valid argument form. So if we're presented with an argument within deductive logic, and we're concerned to evaluate whether it's valid, then what we really need to know is whether it's an instance of a valid argument form. Argument forms are valid if they have no counterexamples. So we've sort of shifted the burden now. In order to evaluate an argument, we need to evaluate whether the argument form is valid. But of course, this requires us to define a counterexample, and so this then brings us to the third and final definition. A counterexample is an instance of an argument form that has all true premises and a false conclusion. So, to evaluate whether an argument is valid, we need to evaluate whether its form is valid. To evaluate whether the form is valid, we need to establish whether there are counterexamples. A counterexample to an argument form is an instance of that form that has all true premises and a false conclusion. So how do we identify the form of an argument? Well, we start by looking for these special terms that we've emphasized earlier in the lecture. Things like or, if then, and not. So let's return to an argument that we've already seen. If David is a philosopher, then he is not a banker. David is not a banker, therefore David is a philosopher. And this was something that we interpreted, or translated I should say, as P horseshoe gate Q, second premise gate Q, and the conclusion was P. This, it turns out, is an invalid argument form. It's an invalid argument form. Even if all the premises are true, the conclusion might still be false. To see that this is an invalid argument form, I'm going to give you another argument, and I'm going to try and convince you that this argument has the same form as our original argument, and also that the new argument has all true premises and a false conclusion. So here is the new argument. If David got an A, then he did not fail. David did not fail, therefore David got an A. There are two simple sentences occurring within this argument. David got an A, David failed the exam. So we can allow P and Q to denote these two simple declarative sentences. And if we complete the translation, if we translate our argument from English into the symbolic language, then we get the same result as we have above. So that tells us that these two arguments have the same form. Two arguments have the same form if, in translating them into the symbolic language, we end up with the same outcome, the same result. Or maybe a slightly different way to say it, since both of these arguments have the if-then in one of the premises, since both of the arguments have a secondary premise which is identical to what comes with the then part of the if-then sentence, and since both of these arguments have the same sentence that's associated with the if as the conclusion, then they have the same form. Okay, so hopefully now you're satisfied that these two arguments have the same form. The second thing I said I needed to do was convince you that the second argument can have all true premises and a false conclusion. So to illustrate this, let's reflect on my performance in high school art, which was a fairly standard kind of course. So it was one where if you got an A, then you did not fail. That's true, of course, of most college or high school classes. If you get an A, then you certainly didn't fail. So the first sentence was true of my experience in high school art. It was also true of my high school art experience that I didn't fail. I didn't fail the course. So the second premise here is true. However, I wasn't very strong when it came to art at high school, and so I didn't manage to achieve an A. So the conclusion here, David got an A, is false. So we have all true premises and a false conclusion. If we look back at the definition of a counterexample, then we now see that our argument at the bottom left of the slide is a counterexample to the argument form that we're concerned with. It's a counterexample because it has all true premises and a false conclusion. Since the argument form has at least one counterexample, then we know that the argument form is invalid. It's not a valid argument form because it has counterexamples. It's an invalid argument form. And since it's an invalid argument form, then any argument that has this form is invalid. So this tells us that the first argument, if David is a philosopher, then he is not a banker. David is not a banker, therefore David is a philosopher. That argument is invalid because it's an instance of an invalid argument form. And we know that the form is invalid because we've just seen a counterexample. Whether arguments in deductive logic are valid or invalid depends on whether their forms are valid argument forms or invalid argument forms. And this depends on whether we can find or discover counterexamples. Now, one limitation that might have occurred to you already here is that if we haven't found a counterexample, then we might be unsure whether our failure is explained by the absence of counterexamples or whether it's explained by our failure to look in the right places or think of the right kinds of arguments. So if you're trying to find something, then you might always be uncertain as to whether your failure to find it is because you haven't looked in the right places or whether you failed to find it because it's just not there. We have the same problem here with counterexamples if our method involves searching through all possible arguments to see if there are counterexamples. So what we need is a more systematic way of identifying whether counterexamples exist or not. And our symbolic language can achieve that once we recognize two additional features of the language which so far we haven't made explicit. One of these features of our language is that all sentences are presumed to be either true or false. Any sentence, whether simple or complex, in our symbolic language is either true or false. That's the first feature of the language, which turns out to be very important. The second feature is that our operators, those special terms like and, or, not, if then, these are what's called truth functional, which is to say, if you know whether the simple sentences are true or false, then you can determine with certainty whether complex sentences that involve these special terms are true or false. So to illustrate the simplest example, let's take our not operator. And what we see with our not operator is that if a sentence is true, then the negation of that, or saying not that sentence, that new sentence is false. Or alternatively, if our original sentence, P, is false, then the negation of that, or saying not P, that sentence would be true. So if P denotes David is English, for example, and if the sentence David is English is true, then negate P, it is not the case that David is English. David is not English. That would be false. If I tell you it's true that David is English, then you can tell me that the sentence David is not English is false. And similarly, if we have a sentence David is Australian, and we suppose that that is false, then the sentence David is not Australian would be true. If David is Australian is false, then David is not Australian would be true. So that's what we have here on the slide is known as a truth table. It tells us whether a sentence, not P, is true or false, depending whether the original sentence P is true or false. We can complete a truth table for all of our special terms, all of our operators. And this is a hugely important step in terms of understanding deductive logic. So let's set about completing this truth table for our key operators, our key terms. And we start by filling out what are known as the base columns. These are the columns beneath our simple sentences. So we need two simple sentences in this case, P and Q, because we're interested in complex sentences that have as their components two simple sentences. So the convention for completing these base columns is to start with the right-handmost base column, so that's the Q column, and then alternate true, false, true, false. Then we move one column to the left and double the number of trues, double the number of falses, and work down the table, so we get true, true, false, false. What we've accomplished here in completing our base columns is every possible combination of values for our simple sentences. So if we have, as in this case, a pair of sentences, then either both are true, or both are false, or the first is true and the second is false, or the first is false and the second is true. We can now start filling in the rest of the table. So let's start with the AND column, denoted with the small dot. And to help us, let's consider two simple declarative sentences, which we'll denote with P and Q. Annie is a doctor, Elise is a doctor. And so, of course, the conjunction, the AND sentence here, would be translated perhaps most naturally as Annie and Elise are doctors. So let's suppose, starting with the top row, that it's true that Annie is a doctor. And let's suppose that it's true that Elise is a doctor. What then would we say about the sentence Annie and Elise are doctors? Would we say it's true or false? Hopefully you agree that we would regard that new sentence with the AND as being true. So what's happening in our symbolic language actually tracks or is consistent with the way in which AND sentences work in natural language, work in English. So if both parts here are true, or more technically both conjuncts are true, then the conjunction is true. Let's move down to the second row. And so now we're supposing that it's true that Annie is a doctor, but we're supposing it's false to say that Elise is a doctor. So Elise is not a doctor. The sentence Elise is a doctor is false. What, in this case, would we say about the sentence Annie and Elise are doctors? Hopefully, it's clear to you that in English we would probably regard the conjunction, the AND sentence, as false. And that's the way we regard a conjunction in our symbolic language if it has one true premise and one true conjunct and one false conjunct. And the same is true if we reverse the order here. So if the first conjunct is false and the second conjunct is true, then we regard the conjunction as false. Similarly, if it's false that Annie is a doctor and false that Elise is a doctor, then within English, I think most of us would recognize that the sentence Annie and Elise are doctors is false. And that's what we get in the symbolic language. So a quick way to summarize these results for the conjunction, for the and sentence, is that a conjunction is true if both conjuncts are true, but otherwise the conjunction is false. Let's move on to the or sentence. And these are known within logic as disjunctions. And the P and the Q are known as disjuncts. And this time let's work from bottom to top. Scratch that. We'll work from top to bottom again. Okay, so now we have the sentence either Annie or Elise is a doctor. And we're supposing that it's true that Annie is a doctor and it's true that Elise is a doctor. You might find yourself somewhat conflicted about how to evaluate the sentence either Annie or Elise is a doctor if both P and Q are true. And this is because the conflict arises because it turns out that in English, or sentences are ambiguous. There is what linguists call an exclusive or and an inclusive or. To illustrate this idea quickly, suppose you ask a friend if they would like to come to your house for lunch or dinner. Suppose that's the invitation. I think most of us would interpret that as an invitation to come either for lunch or for dinner, but not for both. So we're excluding the possibility of coming for both meals. Often it seems when we make people these kinds of offers, what we're saying is one or the other, but not both. We could go to the movies or we could go shopping, but I'm not suggesting we go to the movies and go shopping. So that's an exclusive use of or. But now suppose you're ordering coffee and the barista asks if you want cream or sugar. I think most of us would interpret that question inclusively. In this case, it seems that saying that you want both cream or sugar is quite within the bounds of social respectability. We don't understand the question as meaning you can have cream or you can have sugar, but you can't have both. So some or sentences and questions are exclusive, some are inclusive. And that's relevant to our logic here because it means that we have some choice to make when it comes to a disjunction, an or sentence, where both disjuncts are true. So the convention within deductive logic is to treat or sentences inclusively, which means that or sentences are true when both disjuncts are true. The rest of the truth table for disjunction, I think, follows English much more closely. So if it turns out that Annie is a doctor, but it's false to say that Elise is a doctor, then I think most of us would regard the sentence either Annie or Elise is a doctor as true. And similarly, If Annie is not a doctor, but Elise is, then again the sentence either Annie or Elise is a doctor would turn out to be true. Suppose that you remember that one of them is a doctor, but you don't remember which. So I think you would regard yourself as saying something true if you were to say either Annie or Elise is a doctor. Finally, we get to a disjunction with both false disjuncts. So what would we make of the sentence either Annie or Elise is a doctor? If it's false, to say that Annie is a doctor, and false to say that Elise is a doctor, hopefully it's clear that in that case we would regard the disjunction as false. So we can summarize this column as a disjunction is false if both disjuncts are false but true otherwise. This then brings us to the final and perhaps most difficult column on the truth table, the conditional. Suppose that we consider the sentence, if you study, then you will pass. If you study, then you will pass. And suppose it's true that someone studies, and suppose it's true that they pass. Maybe we regard that as evidence that what was initially asserted when someone said, if you study, then you will pass, is true. Maybe that's a reasonable way of understanding if-then sentences in English. But certainly within our symbolic language, we regard a conditional sentence, an if-then sentence, as true if both parts of it are true. We use the word antecedent to pick out the bit that precedes the horseshoe, and we use the word consequent to pick out the bit that follows the horseshoe. So in this case, P is the antecedent and Q is the consequent. So if the antecedent and consequent are both true, then within our symbolic language, the conditional is true. But suppose I say, if you study, then you will pass, and suppose you do go away and study, and suppose that actually you do not pass, so it's false to say that you passed. What would we think about the original conditional sentence in that case, about my assertion that if you study, then you will pass? I think in this case it's pretty clear that in English we would say that I had said something false. If I tell you, if you study, then you'll pass, and it's true that you do study, but false that you pass, then it does appear that I've said something false when I've uttered the phrase, if you study, then you'll pass. This is reflected in the symbolic language. And so the conditional comes out false if the antecedent is true and the consequent is false. The final two cells here, the final two rows for the conditional, are perhaps the least faithful translations from English of everything that we've talked about. And there are reasons as to, I think, why the translation here is difficult. But rather than go into those reasons, I'm just going to state that a conditional sentence is true if the antecedent is false. So that you might choose just to commit to memory. You might just decide, I'm not going to worry about the reasons, I'm just going to commit this fact to memory. If you are curious to learn more about the reasons, then you will find things either in the text or you could search online for suggestions. We've now reviewed everything that we need to do in order to be able to finally evaluate arguments and establish whether those arguments are valid or invalid within deductive logic. So let's start by returning to an argument that we looked at much earlier in the lecture, and you'll see it there at the top of the slide. And let's evaluate that argument using the truth table method. So we start by completing the base columns, which are the truth values, whether something is true or false, for the simple sentences P and Q. And so if we fill out the truth tables for the base columns, then this is what we get. Now let's move over all the way to the right-hand column, the conclusion column, which is just the sentence represented by the letter P. And so what we're asking in each of these four cells, on each of these four rows, is the sentence, in this case P, true or false, given the values, whether something is true or false, in the base column. So we're asking here about P. So in that first row, we see that P within the base columns is true, so we know that P is true. If P is true, then P is true. And the same is correct for the second row. P is true for this row, and so we fill in true for the final column. In the third and fourth rows, P is false, and so that's how we complete the truth table for the concluding sentence. Moving one column to the left, we see now that the sentence we're concerned with is not Q, or the negation of Q. So the question we're concerned with this time is not Q true or false if Q is true for some rows or false for others? And hopefully what you'll remember is that if Q is true, then not Q is false. And as we've pointed out, there really shouldn't be anything very mysterious about that. That is quite in line with how we think the word not works in English. So on the first row, Q is true, so not Q is false. On the second row, we'll see in the base columns that Q is false, so not Q is true. In the third row, we see within the base columns that Q is true, and so not Q is false. And then in the fourth row, we'll see that Q is false, and so not Q is true. So this now just leaves us with one more sentence to evaluate for purposes of completing the truth table, and then once the truth table is complete, we can consider whether there are counterexamples, and that will help us, or that will determine for us, whether the argument form is valid or invalid. Now this final sentence is a little more complicated. We have a conditional, and furthermore, the consequent of this conditional is a negation. So there are a couple of things to keep track of here, and in order to try and reduce the chances that we make mistakes, it's perhaps useful first to reflect just on the truth or falsity of the consequent, and then proceed to evaluate the truth or falsity of the entire sentence, the conditional. So that's what we'll do. So we're just going to concern ourselves for the time being with the consequent. And the consequent here we see is the negation of Q or not Q. Well, we've already filled out a column like that, so it's just a matter of copying over. Not Q is false for the first row, true for the second, false for the third row, and not Q is true for the fourth and final row. Now we're in a position to evaluate the conditional. And if you remember from previous slides, a conditional is false if the antecedent is true and the consequent is false. But otherwise, the conditional is true. I'll repeat that. A conditional is false if the antecedent is true and the consequent is false, but in all other cases, the conditional is true. Well, the only row on which we have a true antecedent and a false consequent is the first row. On every other row, that is not satisfied. On the second row, the antecedent is true, but the consequent is also true. We can see that from what's written or typed in smaller font under the consequent. And then in the third and fourth rows, the antecedent, which is P, is false. So it's only on that first row that we have a true antecedent and a false consequent. So the conditional turns out false. And then for all other rows, the conditional is true. So we have now completed the truth table. We relied on the truth tables for negation and conditional, which we'd already introduced. And beyond that, it's just a matter of considering whether P and Q are true or false for a given row and how that affects the truth value of the sentence that we're evaluating. The final step to establish whether this argument form is valid or invalid is to ask whether there are any rows which have all true premises and a false conclusion. That's our definition of a counterexample. All true premises and a false conclusion. So there are only two premises in this argument form. Those are here the third and fourth columns of our table. The conditional sentence is the first premise. The negation of Q is the second premise. So we're looking for a row where those two sentences are both true. And then we're looking to see if on the same row the conclusion is false. If we find an example of that, we have a counterexample. Well, on the first row, the premises are all false. So that doesn't provide us with a counterexample. On the second row, the premises are all true, but the conclusion is also true. So we don't get a counterexample there. On the third row, not all the premises are true, so we're not going to get a counterexample there. On the fourth row, we do get all true premises, and we get a false conclusion, so the fourth row does provide us with our counterexample, which tells us that the argument form is invalid, and hence that any argument which has this form is an invalid argument. Now, it shouldn't surprise us that the truth table method renders this result, because we'd already used an alternative method to evaluate the argument form, and we'd already concluded that it was, in fact, an invalid argument form. The truth table method enables us to evaluate any argument whatsoever that can be expressed within the language of deductive logic. But in this course, we're just going to introduce three argument forms that are important and which are valid argument forms, and then we'll introduce three valid forms that are invalid argument forms. And for two of the valid forms and for two of the invalid forms, we'll use the truth table method to show that the argument forms are in fact valid or invalid. So the first valid argument form I'm introducing is known as modus ponens. And it's an argument form that has a conditional sentence as its primary premise, the antecedent of that conditional as the secondary premise, and the consequent of the conditional as the conclusion. So that's modus ponens. Any argument which has this form is an instance of modus ponens. Let's see that it is actually a valid argument form using the truth table method. The base columns are already filled out in the convention that we've already introduced and utilized. The truth table for the conditional, we've said it is true for every pair of combinations for P and Q except when the antecedent is true and the consequent is false. That's to say, when P is true and Q is false, then the conditional is false, but in all other instances, the conditional is true. P is the next premise, and this of course is just going to replicate what we see in the base columns. So P is true on the first two rows and false on the third and fourth rows within the base columns, so it's going to have those same assignments or values within the body of the truth table. And then finally, Q is again just replicated from the base columns. If we look at the base columns, then Q is true on rows 1 and 3, false on rows 2 and 4, so that's how we evaluate Q when it appears as the conclusion. If we look along all 4 rows, then the only row where the premises are all true is the first row. On the first row, the conditional is true and P is true. So we have all true premises. But the conclusion is also true. So there are no counterexamples within this truth table. On every other row, 2, 3, and 4, there's at least one false premise. So not all premises are true. So there are no counterexamples to modus ponens, which shows us that this is a valid argument form, and hence that any argument which has that form is a valid argument. The next argument form I'm introducing is modus tollens, which also has a conditional as its primary premise, but this has the negation of the consequent as its secondary premise and the negation of the antecedent as its conclusion. At this point, I would encourage you to use the truth table method to convince yourself that you understand how the truth table method works by showing that modus tollens is a valid argument form. The third argument form we're introducing is disjunctive syllogism. Disjunctive syllogism has as its primary premise a disjunction, which shouldn't really surprise us, given the name of the argument form. The secondary premise is the denial of one of the disjuncts. It can work either way. We deny one of the disjuncts and then we conclude with the other disjunct. But here I've used the first disjunct within the secondary premise, and we've got the denial of that, which is P, and so the conclusion here is the other disjunct, which is Q. So let's quickly walk through the completion of this truth table. The base columns again are already complete. If you refer back to the truth table for a disjunction, you'll see that a disjunction is false if both premises are false, but otherwise it's true. So it looks like that. Disjunction is false if both disjuncts are false, but otherwise it's true. Secondary premise here is the denial of P. Well, if we look at the base columns, P is true on rows 1 and 2. So the negation of P is false on rows 1 and 2. And P is false on rows 3 and 4. So true on for not P for rows 3 and 4. Finally, the conclusion is Q, and that's just going to replicate what we have in the base columns: true, false, true, false. If we look at these 4 rows, we see that the only row that has all true premises is the third row. On the third row, all the premises are true. Maybe I should have emphasized this earlier, but the base columns are not the premises. The base columns are something different. Our premises are, in this case, the third and fourth columns. So when looking for counterexamples, we can ignore the base columns altogether. So the only row on which all the premises are true is the third row, but that also has a true conclusion. So we have no counterexamples. So this is a valid argument form. Turning now to the invalid argument forms, the first one I'm introducing is known as affirming the consequent, and we'll see in just a moment why it has that name. The primary premise is again a conditional sentence, so in that way it's like modus ponens and modus tollens. But this time, the secondary premise affirms the consequent. It asserts or affirms the consequent, hence the name of the invalid argument form. The conclusion for this argument form is the antecedent of the original conditional. Let's complete the truth table. The truth table for the conditional. Hopefully by now we're remembering a conditional sentence is false if the antecedent is true and the consequent is false. But for all other assignments, the conditional is true. For the secondary premise, we just need to replicate what we see under the Q column of the base columns. So Q is true on rows 1 and 3, false on rows 2 and 4. So moving that over, this gives us the truth table for the secondary premise. And finally, the conclusion is just P. So again, we're just directly copying from the base columns. P is true on rows 1 and 2, false on rows 3 and 4, and so here is the truth table for the conclusion of our argument. If we look down the 4 rows, the first row has all true premises, but also a true conclusion, so no counterexample there. The second and fourth rows have at least one false premise, so we know that they don't provide us with a counterexample. The third row, however, has all true premises and a false conclusion. So the third row gives us a counterexample. And what that tells us is that affirming the consequent is an invalid argument form. So we've just used the truth table method to show what I'd already given you reason to expect a few moments ago, namely that this is an invalid argument form. It's invalid because it has a counterexample. That's to say, there is a way of assigning truths or falses to the simple sentences within affirming the consequent, whereby all the premises come out true and the conclusion comes out false. The second invalid argument form we're introducing is denying the antecedent, which also has a conditional as its primary premise. The secondary premise denies the antecedent, hence the name of this argument form, and the conclusion here denies the consequent. As I did on the previous slide, I'm going to encourage you at this point to use the truth table method to convince yourself that this is an invalid argument form, and thereby also give you some important practice in filling out truth tables. The third invalid argument form that we're introducing in the class is known as affirming a disjunct. And we can see here that the major premise, primary premise, is a disjunction, which we're denoting P wedge Q, or P or Q. The secondary premise, the minor premise, is one of the disjuncts. In this case, I've used P. And the conclusion for affirming a disjunct is the negation of the other disjunct. So in this case, the negation of Q. This is an invalid argument form, so what we should see when we complete the truth table is a counterexample. So let's see if we find one. You'll remember that the truth table for the disjunction tells us that a disjunction is true if at least one of the disjuncts is true, but false if both disjuncts are false. So it looks like this. In the top three rows, at least one of the disjuncts, so either P or Q, at least one of those is true, so the disjunction is true. In the fourth and final row, P is false, and Q is false, so we don't have a true disjunct, so the disjunction is false. The secondary premise, the minor premise, is P, so here we're just moving over directly from the base columns the truth values for P. So in the top two rows, P is true, and in rows 3 and 4, P is false. So you can see that there's direct correspondence between what we have in the P column in the base columns and now the P column as it features as the secondary premise. The conclusion to affirming a disjunct is the denial of the other disjunct, which in this case is the second disjunct Q. So we need to pay attention to the Q column when filling out the column for the conclusion. When Q is true, not Q is false. When Q is false, not Q is true. So when we finish out the final column in our truth table, it looks like this. Looking at all four rows now, we see that on the second row, all the premises are true. Both premises are in fact true, but the conclusion is also true, so we don't get a counterexample from row 2. If we look at rows 3 and 4, at least one of the premises is false, so we don't have all true premises, so neither of those rows can provide us with a counterexample. But on row 1, at the very top, we see both premises are true. We see also that the conclusion is false. That is the definition of a counterexample. So using the truth table method, we have identified a counterexample to affirming a disjunct, and so that shows us, that proves that affirming a disjunct is an invalid argument form, and hence any argument that has that form is an invalid argument.